that I've been thinking about. So this is mainly my work for my PhD thesis that I'm working towards. So I'll be talking about higher dimensional Legendrians, and so by that I mean Legendrians in contact manifolds of dimensions 5 and above. So the main, just to make sure, just to get definitions. So Legendrian submanifolds are ones that are tangent to the contact hyperplane arrangements. And so in a 2n+1 dimensional contact manifold, a Legendrian is n dimensional manifold. And we will generally see Legendrians using front projections. So that's how they're generally pictured, and they're used to compute their invariance. So for example, in the standard contact structure in the Euclidean plane, a Legendrian is uniquely determined by its image under where you project out the y coordinates. And so you just have the z and the x coordinates. And more generally, in the 1z space of a manifold, the front projection is defined by just projecting out the cotangent directions. So you go from J1M to R cross M. Okay. So that's generally how we picture them. And so just the title slide, I had 2 pictures. So these are sort of front projections of the Legendrian unknot. This is in dimension 3, and this is the Legendrian 2-sphere unknot in just R5. It's just the flying saucer. Right. So as I mentioned, my focus is mainly on Legendrians in high dimensions. So I'm looking at n-dimensional submanifolds in 2n+1 dimensional, and n is bigger than or equal to 2. And a motivating question is, how do you construct interesting Legendrian submanifolds and compute their invariance? And so the reason this is an interesting question is because, you know, for constructions of contact manifolds, we'll usually use lower dimensional Legendrians, and then surgery on them produces contact manifolds. This has been very successful for understanding contact structures in dimension 3. And so in higher dimensions, that's one thing that's generally interesting. And so since we are focusing on surgery questions, we'll focus on Legendrian spheres. Okay. And so just to recap some existing work in this direction. So this is not an exhaustive list but this is sort of that are relevant in this direction. So Ekholm, Etnaer, and Sullivan in 2006, they were able to define the Legendrian contact homology invariance. They were able to generalize the Chekhanov-Eliashberg DGA invariance to higher dimensions, and they used that to produce some interesting families of Legendrians. So one thing they did produce is an mutually non-isotopic infinite family of spheres, and their idea was sort of a higher dimensional notion of stabilizing a Legendrian. So what they did was they sort of took 2 copies of the unknot and then just pushing one's front through the other. That's a notion of stabilization. And then connecting the cusps via an arc and then repeating this construction, they were able to show that this produces a mutually non-isotopic infinite family. And then, so these are all infinite family of spheres. And then another thing that has recently come up is Casals and Zaslow have described this n-weave calculus for n equals 2. So in the 1z space of a surface, you can take some combinatorial data on the surface and use that to get interesting Legendrians in the 1z space of the surface, and that also produces spheres depending on what kind of combinatorial data you start with.
Sorry, a basic question that you have sort of addressed. What is an unknot in higher dimensions?
Right, so by the unknot, I meant you can take the definition to be you start with the unknot in dimension 3, and then you can sort of spin it around. So you could take half of it and then spin it around, and that gives you an unknot in the higher dimension, and then you repeat this construction.
So have it every time and then spin it in the extra dimension?
Right.
Thank you.
Thanks. So that's what I mean by the unknot. Okay. And then another construction that's going to be particularly relevant for our talk is this is Ekholms construction, which is taking a double of a Lagrangian filling of an unknot of a knot, and then sort of taking a Legendrian lift of it. So just for more details on what Ekholms construction looks like, so consider a Legendrian knot in an R2n+1 slice, and then consider two disk fillings that live in a sort of symplectic R2n, and then you can join them, and then there's a well-defined notion of taking a Legendrian lift once you have Lagrangian disks on either side. And if you lift them, then you get a sort of two disks joined at their boundaries, so you get a sphere. Okay, and you can take two distinct fillings, and so that and the notation is lambda fg. And so what Ekholm showed is that if f and g are different, so if you take distinct Lagrangian fillings, then Ekholm and Murphy, so as an addendum to his paper, showed that is always loose. And then later for this construction, like if you take the same fillings on either side, Court and Ekholm a couple years later showed that is always isotopic to the unknot. So in some ways that is that sort of shows that, like, if your motivation is to construct interesting, like an infinite family of fillings, no matter what data you choose, what k you choose and what f you choose, you always end up with the unknot for this construction in R2n+1. So this sort of gives us a direction that will not work to produce a lot of examples. So that's like the general Ekholms construction. And are there any questions at this point about anything I've spoken about? Okay, all right. So I'll move forward, and so my idea is to try and understand, so similar input you can use for an open book decomposition of a manifold, and what can that tell us about Legendrians you can construct in a sort of similar way, in philosophically in a similar way to Ekholms construction. So just some background on open books and stabilization. So we know that every closed contact manifold has a supporting open book decomposition. So what I mean is that there's a Liouville manifold, so lambda is the primitive, and a symplectomorphism on W, such that the contact manifold is contactomorphic to this construction where you take the mapping torus of W with respect to the symplectomorphism and then cap it off with the boundary crossed with two disk. And and the usual notation is to call this W as the page of the open book. Okay. So given that contact manifolds are supported by open book decompositions, there's a notion of a stabilization. So the open books are not unique, and you can get different open books that support the same contact structure in some way. So what you can do is, so given a Lagrangian disk inside the Liouville manifold, whose boundary is on the boundary of the Liouville manifold, you can attach a Weinstein n handle to the boundary of the page to get a new Liouville manifold. And so that gives you a Lagrangian sphere now. So this is sort of a schematic for what is going on. So this was your manifold earlier, and this is your Lagrangian disk inside the page. And so now you can attach a Weinstein n handle along its boundary, and what you get is WL, which is W with an n handle attached, and you have a sphere in there, which is just the disk plus the core of the handle. And you can define a new open book where it's this page, and you modify the monodromy by doing a Dane twist or a Dane serial twist in high dimensions along this Lagrangian sphere. And it's a folk theorem, but that it doesn't change the contact structure. So like MC is contactomorphic to this, which was contactomorphic to this original open book, continues to be contactomorphic to this stabilized open book. And so this is generally known, but just an understanding of, like, it was helpful for me to understand this from lecture notes by Otto van Coort, what this process is and how this contactomorphism is actually seen. So that's a good resource if anyone's interested. Okay, right. So we have this notion. So given an open book for a contact manifold, we can stabilize it. Okay, so that now tells us how. So this is how I wanted to generalize or Ekholms construction to general contact manifolds. So you have some supporting open book for a contact manifold, and you have a properly embedded Lagrangian disk inside the page. So the first thing you can do is you can take you can have the open book, and you can take 2 copies of the disk in different pages and sort of join them through the binding. Now, there are some technical details as to how exactly you join them, but that's the main idea, that if you join them through the binding and if you manipulate the contact structure, then take the Legendrian lift, you get a well-defined Legendrian sphere and the manifold. So that is the first construction. That's I call that S join because you're joining them. And the second construction is is the sphere we just talked about, is if you stabilize your open book along the boundary of this Lagrangian disk, then you get a sphere, which is the disk plus the core of the n handle you attach, and that gives you a sphere, which we can call the stabilizing sphere, and I'll call that S stab. Okay, so these are my 2 constructions in general contact manifolds, where the input is a Lagrangian disk in the page of a supporting open book. Okay, and so the first finding is that these 2 constructions give isotopic Legendrians. Okay. So there's some technicalities to first make that statement, because to construct an isotopy, you have to sort of stick to the same manifold. And this thing about stabilization is the way we defined it. We know that MC is contactomorphic to both the open books, but it can be an abstract contactomorphism. And so we have to sort of understand the contactomorphism in the stabilization in the same manifold. So we have to sort of see both of these in the same manifold, not contactomorphic ones, and then sort of try and construct an isotopy. So that's the first technicality in this theorem. So a way around that is to understand stabilization, this process, as an embedded operation. So there's a modification of this open book. You try and understand it as a surgery, or as like a cut and paste operation in the manifold. If you do that, what you can do is then isotope the join thing out of the region that's being modified, and then sort of see the both of them in the same manifold. And the next step to prove the isotopy, and I'll talk about this in more detail, is to reinterpret this notion of a Dane twist as a Legendrian surgery, and that's also well understood in general, but understanding that local model well and sort of doing some work with it allows us to actually construct the isotopy explicitly between these 2 Legendrians.
So in the join,
yeah.
sorry.
No,
In the join operation, is there do you have a preferred leaf to pick from the book to sort of to get the second component, or how does it work?
No, so you can use any,
and they all give the same thing,
right? Yeah.
Thank you.
Yeah, that's going to be relevant to like what these spheres are. Okay, so I'll just talk a little bit about how to see stabilization as an embedded operation. So this idea, there's a paper by Vertesi and Licata called Foliated Open Books in 3 dimensions, and where they talk about sort of cut and paste on open books, and this idea is mentioned there. And so the point of this is to generalize that and to understand that. And so that's what I try to do. And so how does it work? So L lives on a page and it's properly embedded in the open book, right? So what you can do is you can take a neighborhood out from the manifold, And what that neighborhood can look like is it's just a neighborhood of L from some pages. And then on the other pages, it's just a neighborhood of the boundary. And if you think about it, the open book sort of goes around and L lives here. So if you take out a neighborhood of L from some of the pages and just boundary from the other pages, you can get a neighborhood of L out. Okay, right. And so this is how those pages get modified. You just remove the neighborhood of L. And so this is the page, and the middle part's gone. And then you've removed the sort of the boundary from these pages. And what you then do is, using Darboux-Weinstein coordinates, we know that any Legendrian in two different contact manifolds, you can sort of identify their boundaries in a canonical way. The contact structures in their neighborhoods can be sort of assumed to be the same. And so what you do is you know that the 2n+1 sphere is supported by an open book where the pages are the unit cotangent bundle on the n sphere, and the monodromy is a Dane twist on the core of that page. So you can take a sort of what I'm defining as like a transverse disk. So if you think just if you fix the coordinates on the core disk and just look at the cotangent direction, that gives you a disk in the unit cotangent bundle. And that's a Lagrangian in the page, and it's a Legendrian in this manifold. And you can identify it with a neighborhood here, and you can do the same kind of operation to get a neighborhood in here. And then you glue in the complement of the neighborhood of this by sort of twisting the pages. And so the idea is you had these pages that came up, and you take sort of the opposite pages and you glue them, and the page gets modified by you're adding an n handle. So that's how you do. And so if you do this operation, that's how the page gets modified. And there's some technical details as to how this exactly works out, but it can be done in a global, nice way. And that modifies the open book, and you can argue that that actually is the stabilized open book. So essentially, stabilization is just cutting out this ball and gluing in the complement from the sphere. Okay. And so once we can do that, we can now see stabilization as like a cut and paste operation, and that allows us to see the join and stabilization spheres in the same contact manifold. Right. And so the next step is to actually construct the isotopy. And so we do the isotopy through understanding how the Legendrian surgery happens. So there's a schematic here, and I'll try to explain this picture a bit. So this picture essentially is a neighborhood of the stabilizing sphere in the pages. So what you can imagine is that everything, this green sort of plane is sort of cutting everything in sort of two halves, and everything here on the right side is getting added after stabilization. So you can imagine that this sort of used to be the boundary of the page, and now you've done a surgery, and now the page sort of extends over this handle. Okay, and in this picture, you can. So you can sort of imagine that the join sphere used to live on this picture as this piece L here and this piece L down here, and they were somehow joined either through the binding or somehow they were joined like this. So this used to be S join, or and you can just sort of move it out, and the neighborhood really is not exactly. And so these sort of annuli are the pages, and this direction is sort of the monodromy direction. So these annuli levels are the pages. And what you can imagine is you've surgered out this bit to perform the Legendrian surgery, and that's what the neighborhood is after the stabilization. Okay, and so if you can take this S join and move it out a little bit, it's still there in the manifold, and this bit that lives here, it's a neighborhood of the Legendrian that's been surgered out and replaced to perform the Legendrian surgery. And so we have this sphere and this joint sphere, and we want to say they're the same. And as it turns out, if you understand this piece well, you can sort of bring this disk piece over to this disk piece. So you can sort of construct a one parameter family of disks that will allow you to sort of move one of these disks to another, and you can also match up the sort of the join parts. And so that allows you to isotope one sphere to the other. And so this deals with understanding these local models a bit better, but that's sort of the idea here, how the Legendrian, how the isotopy happens. Okay. So right, so just to recap, all this was to prove that the joint spheres and the stabilizing spheres are isotopic. Okay. Right, so that's the first result, and so so what I'm working on now is as Sarah's question, it allows us to actually show that this S join, and hence the stabilizing sphere, is isotopic to the unknown. And so what's the idea there? As I said, it doesn't matter which page you choose it on. So you can sort of isotope the pages to be really close, and then the joint sphere is just sort of the disk and a push off, and they're joined. And the idea is, if you have any Legendrian disk, you can isotope it down to a point, and you can isotope it back out into sort of the standard Legendrian disk that's half the unknown. And so those are sort of things I'm trying to work out. And so I haven't claimed it as a theorem yet, but the idea is that that isotopy actually takes that and its push off, and they can actually become the unknot. The motivation is, if you look in lower dimensions, if you take a Legendrian arc and you take its push off and you join them, you can always like do randomized moves and get that down to the unknot. And so these, I expect very strongly that these are all the unknot. Okay. And so another thing I expect to show is, and explicitly, that if you remove a point from the standard contact 2n+1 sphere, that's supported by this open book with just a symplectic ball and the identity monodromy, you can construct an explicit isotopy from the joint sphere to the doubled sphere that was constructed by Ekholm. And so that's a way to reprove and to quote an Ekholm's result that this is the unknot. So yeah, and that's also this deals with sort of understanding these contact homomorphisms a bit well, and so just some technical details need to be written down. So that's also some work in progress, right? And so just to summarize, these are the results, that these Legendrians are the same. They're all unknots, and for the S2n+1 case, this recovers Ekholm court's result that the doubled sphere is always standard. Right, and I'll stop here. Thanks for your attention.
Thank you very much, Agniva. Are there any further questions?
Yes. So with this representation of stabilization within the original manifold, does that mean that you can? Is it just sort of an analogous procedure, or are you saying that you could maybe like construct a family of contact homomorphisms starting with this one and ending with the more classical representation that somehow, like, is there a stronger statement like this, or is it just sort of something that's supposed to describe the same operation?
I think it just describes the same operation. So like generally how the contact homomorphism is shown is like appealing to like a higher dimensional cobordism. Like you see stabilization as adding like for if you take the symplectization, you add a symplectic handle and a canceling pair of symplectic handles. Mm-hmm. So you know that the boundaries stay the same, and as like boundaries stay contact homomorphic, and you use that sort of description. And this is what this operation does is you just do this surgery kind of operation, and you can argue that it gives a compatible open book that's exactly the stabilization that agrees with the abstract description of the stabilization, and hence it has to be sort of the same contact structure, appealing to that result there.
So I guess my question is, when you say it agrees, what do you mean exactly?
So abstractly, you can say that the pages are symplectomorphic, and the monodromy is also corresponds to the same thing. So abstractly, it's the same, and then just appealing to the fact that stabilization preserves the contact structure up to contactomorphism, you can see that this preserves the contact structure. This gives you a contact manifold that's sort of contactomorphic to what you had already. But the modification happened via a surgery, so everything outside you modified stays the same.
Right.
So just for this purpose, to identify these two Legendrians, if you isotope this outside, you know that it's still a Legendrian here. You can sort of talk about these two in the same manifold.
Okay, thank you.
Right, so let's thank Agniva again for his talk.